Hi there. This is one of the Getting Started videos for HL7 FHIR. And this particular video is client-server architecture, including APIs and CRUDS. And my name is Terry Sippel-Schmidt. Let's go through a brief example of what a modern client-server architecture looks like. Over here on the left, we have all different kinds of clients. Maybe one is a cell phone app, maybe another is a patient healthcare record app, maybe one is a very expensive MR scanner. Maybe another is a vital signs recording system. There can be different kinds of internets in between. For example, there can be the internet, which is public. There can be intranets, which are private to a specific institution. In any case, this is always going to be a FHIR API model in between all of the different clients, of which there may be hundreds or even thousands, and the server. Over here, we have a FHIR server, and this is where all of our data is stored. It's stored using the FHIR representation. But if this is a healthcare institution and there are thousands of clients, it probably doesn't look like this. It probably looks something more similar to this. And you've got redundant storage, you've got electrical backup systems and UPS, you've got RAIDs and all sorts of things, so that should there be some kind of an equipment failure, all the data which is being stored in the database server is backed up and isn't lost. Contrast that really quickly with if you have all of your data stored on all of these different clients all over the place, and what a nightmare it would be to make sure that all of these things are stored up redundantly and protected if there's some kind of power interruption. What is an API? API stands for Application Programmers Interface, and an API is how a client and a server communicate and exchange data. In other words, how they talk to each other and they know how to pass information back and forth. APIs are a critical component of FHIR. And furthermore, FHIR uses RESTful APIs, where RESTful stands for Representational State Transfer. And what that means is that the server doesn't need to keep track of what the client is doing. It makes for a much easier server implementation. If the client needs anything else, they just ask again. And how does an API work? Well, there's two components to an API request. One is the request. The second component is the response. Right now, we're going to focus on the request. The request almost always starts at the client. So you have a client, and again, this can be your cell phone app, or this could be a medical record device, or this could be the vital record system. The request almost always starts here, and they're going to send the request via the API over to the server. The server is just sitting here hanging out, storing data. What does it actually look like? A FHIR API request consists of three components. It consists of the protocol. In this case, we're using Hypertext Transfer Protocol, but the S here stands for secure, and just be certain to note that security is optional in HTTP. The second component of this is the URL, or the Universal Resource Locator. The first part of the URL is the server. Who are we going to go talk to? In this case, we're going to go talk to the server on internet, which is happy.phir.org. And we're going to go to a specific subdirectory or a specific location or specific server there, and that's going to be called the base R4 or release 4, version 4 of FHIR. There's other versions, but we're going to focus on version 4 of FHIR for this class. After that, there's the third component. This is what do we want to talk about? We're going to talk about a resource called patient. And this particular question mark is a query string separator. So we're going to talk about patients, and then everything following this question mark is which patient we want to talk about. I usually read the question mark as where. So we're going to talk about patients where the identifier, in this case a patient ID, is equal to 77550099. So let's start at the beginning. We're going to use HTTP to go talk to the FHIR server for release 4 and look for a patient with this patient identifier. And that's how you read a FHIR API request. Let's take a peek under the hood. This particular screen snapshot is a program called Postman, and we're not going to use that, although you're welcome to if you're a software developer. Underneath the hood of every API request is a verb. And what are you asking the server to do? In this case, when we're doing the request for our patient with the identifier of the string given, we're going to do what's called a get, an HTTP get. As well as doing a get, there's a whole different series underneath this API, one of which is called a header. And there's a bunch of different data being transferred back and forth. There's information, for example, like what formats are we going to accept? What is the encoding going to look like? Do we want to keep the connection alive, or do we want to take the connection up and down? How are we going to do authorization? But I have great news for you. Because we're using HTTP and FHIR APIs, you don't need to know this level of detail. Only know that there's all sorts of things going on under the hood, which you don't have to pay as much attention to. In addition to the header, as part of an API, there's also a body. If you're trying to give information to the server, the information is actually going to go into the body of the API call. Before we jump into that, though, let's take a peek at some other RESTful API calls and just show you all the different examples that exist on the internet. The first is Amazon. I went to Amazon and I did a query for N95 masks. So let's take a peek at what that looks like in terms of the API. Here you have a padlock, so it tells you it's using HTTPS. Then we're going to go to the URL or to the host amazon.com. Here's the separator, which will tell you the different query keys. And I don't know Amazon's API, but I can make some guesses. My guess is that the S stands for search, search where, and then the keys that we're going to search for are N95 plus masks. And then there's a bunch of different parameters that Amazon has defined that I have no idea what they mean. But you can see how you can kind of decipher this particular API, which is defined by Amazon. Let's go take a look at the Wall Street Journal API. I go to WSJ.com, and the path that I go to is news. There's also subscription paths. There's all sorts of paths at the Wall Street Journal, but I want to read the news today. And I'm going to click on World News. So I'm going to say, or the API is going to say, go to the Wall Street Journal URL, go to the specific path of news, and then click on World and take me to the top navigation screen. So go to World, where I go to the top navigation screen. So you can see it's just a different formatted API as defined by the Wall Street Journal, but the basics are always the same. So what can you do with an API request? You can do CRUDS. CRUDS is a really useful acronym. It stands for C is for create a new lab report for a patient. R is for read the lab report for a specific patient, get all the data. U is for update the patient's phone number, address. D is for delete. Okay, let's not delete. In healthcare, it's not always a good idea. There are legal implications to delete patient data. What we often do in healthcare is we deprecate. And the difference between delete and deprecate is that if you deprecate data, and a client may have a really good reason to deprecate data, if you deprecate data, the data is still there. It's just that none of the other clients can see it. There's probably some super user with super user privileges who can still see deprecated data, but the normal average client, to the normal average client, that data has been deleted and is gone. It's just invisible. Finally, the S in CRUDS is for search. Give me a list of all the patients. Give me a list of all the reports for that patient. So S is for search. You're often going to see these icons. You'll often see the pencil for create or edit. You'll also often see the R, maybe it's a book. For the read, you'll see this refresh symbol for update, and you'll see this garbage can for delete. Why I couldn't find a meme that had the S on it, I don't know, but you often see the magnifying glass for search. So we talked a little bit about underneath the hood, and the reason I want to go into this is because your book spends a lot of time on this, and I think the textbook does a good job of explaining this. However, I wanted to link it back to CRUDS. So in terms of HTTP verbs, a create is a post, a read is a get, an update is a put, a delete is a delete, but please don't delete on the server, please deprecate, and a search is also a get. So when the textbook refers to all these HTTP verbs, this is how you relate them back to CRUDS. Let's talk about a couple of those. Let's talk about read and search. Read and search is asking, the client is asking for information stored on the server. These are going to be an HTTP verb, both be an HTTP verb of get. In this particular example, for either a read or a search, there's no data being sent from the client. It's only a question in the API. The response from the server will contain the FHIR instances and the status. So down here, we have an example of a patient healthcare record, and someone is requesting for a patient's lab values. We'll assume that they have access, and it's going off to the server, and the server response is returning those lab values back to the client so that they can visualize them on their computer system. Another example, or another part of CRUDS, is create and update. Create is a post and update is a put. Note that in a create or an update, the data is actually going from the client to the server, as opposed to what we just saw in a read and a search, where the data is returned from the server back to the client. In this case, for a create or an update, the data being structured by the client is structured as what's called a FHIR resource, or a template for how the data should look and what data should be in there. The data is being sent as what's called JSON, or a FHIR instance. So it may be in the template of FHIR. The specific numbers, the 78, the 80, the 19, is an instance for a specific patient for a specific result for vital records. And then finally, we're going to take this information, we're going to send it to the server, and finally the server is going to give us a response back. It's not going to give us data back, it's just going to give us a response, usually success or failure. So we haven't completely made it through the circuit yet. We were focusing mostly on the request, although we did talk a little bit about the response, but let's go into a little bit more detail about this message coming back from the server to the client. The response is the answer from the server. It contains the data if you were doing a read or search. The format of the data coming from the server back to the client is in the format of a FHIR request template. The content of the actual response is the FHIR instance for a particular patient or a particular lab value. FHIR specifies the data as XML, JSON, or Turtle. In our class, we're going to focus strictly on JSON. The other thing that the FHIR server also always returns is a response, an HTTP response status code. There's hundreds of HTTP response status codes, and you should feel free to go look them up on Wikipedia or any one of other sites. The ones that you need to know are listed here. In general, 200 is good, 400 is bad. So you're going to see a lot, we hope, of code 200, which means okay. So if you're creating something, you're going to see a 201, which means that was created on the server. A 202 means the server accepted it. Maybe it got queued. A 202 is similar to a 200 okay, but maybe it got queued, maybe it was deprecated instead of deleted, but basically it was accepted. Not quite the same as okay, but pretty similar. If you get a 400, that means that it was a bad request. They don't know what you want. The server doesn't know what the client wants. Maybe the API string was formatted incorrectly, not sure, but the server doesn't know what to do with it, so it just says 400 bad request. If you get a 401, that means you weren't authorized to send anything to the server to begin with. It's a security issue. All right, let's go back to our Postman response because we can see more things in Postman. Here you can see that we did a get. So we were doing a request or a read, and we were going to the happy server again, to R4 again, and we're asking for a patient with a given name of Johns and the family name of Hopkins. And you can see here that our status code, this is the response from the server, it's a 200. Okay, that's good. 200 is always good. And you can see here, this is the JSON response. So what you'll see in the body of the response, the return, is because we were doing a request, is the actual JSON and the answer. And you can see we requested patients, and sure enough, it's going to give us a patient back. That's good. Sometimes it's best to compare and contrast where you've been and how other systems work so that you can understand the system that you're working with. Let's take a step back in time and look at how HL7 version 2 messages. So this is a predecessor to FHIR. We're specifically going to talk about how to update a patient. A patient comes into a primary care office, and sure enough, the patient's address has changed. Or maybe it's their date of birth. Their date of birth was wrong. Date of birth is important. We have to propagate that message to all the different clients in the entire hospital. So we're going to change the patient date of birth at the admissions desk in the primary care office in the electronic healthcare record. The EHR is going to send a message to something called an HL7 version 2 interface engine. This is going to change the protocol, and it's going to change the content of the message because unfortunately, the templates in HL7 version 2 just aren't as solid as FHIR. So there's a lot of different systems that need a lot of different information. So we're going to do some protocol changes on this system, and we're going to move a lot of data around so that all the receiving systems are able to understand it. Over here, this date of birth change, maybe it'll go to the MR scanner. It's going to go to a lot of different databases and record systems, and maybe it'll even go to a vital record system that's being used in an ICU somewhere. Again, there are hundreds, maybe thousands of these clients out in a hospital system. What happens if one of those is turned off when this record message goes out? What happens if one of them is in the middle of a backup? What happens if one of the disk drives has failed? There's some redundancy built into this HL7 interface engine, but at the end of the day, trying to keep all these systems synchronized exactly for every patient, for every piece of information, when you don't even know what is necessarily in all of these databases or what format they use, it's difficult to be extensible and to continue. The corollary to that is that this is how the world works today, and it actually works fairly effectively. It just requires a lot of maintenance. All right, let's recap. APIs, Application Programmers Interface. It's how a client and a server communicate, including in FHIR. It's how they communicate and exchange data. It's how they talk to each other and pass information back and forth. It's bidirectional. Typically, the data is stored and maintained on the server in one place. That's really important. All the data is stored, the gold standard is in one place, not over thousands of different clients. Whenever the client wants, it can ask for the data, it can create more data, or it can update data. Don't forget the CRUDS acronym. The client asks a question or command, and it provides new information or an update via an API request. That's step number one. The server returns an answer, specific instances, and the status, hopefully a 200, something starting with 200, via an API response. That's the second half of the handshake. In our case, we're going to use JSON as the answer format. FHIR resources are the template. They're defined in the FHIR standard for all the content and the format of the data. FHIR instances are specific to a patient or to a report, but they're concrete occurrences of a specific template. Finally, don't forget that HL7, the world that we're coming from, used to spray messages, well, it still does, sprays messages across hundreds to thousands of systems in the hospital. We hope that the receiving system handles it correctly and is able to ingest it. All right, next steps. Let's go build some FHIR APIs using an application called ClinFHIR.